So at the time of its suggestion, the wave model of light was incapable of explaining all light behaviors. Um, so additional work had to be done in this area of study. The emission of light from hot objects, otherwise known as blackbody radiation, this is one thing that we'll be covering in this lecture, and the emission of electrons from metal surfaces on which a light has been shined. This is known as the photoelectric effect, and we're going to look at both of these in this lecture. So blackbody radiation basically refers to the difference between a cool object and its appearance versus its appearance after or as it's being heated. So basically, solids, when they're heated, they usually glow some color type. So, you've heard of something called, a red hot coal or a red hot stove. You might have also heard of, white hot light. So, these things come from heating a stove or maybe like a bright light bulb or things of that sort. Now, the object's color or the wavelength distribution, what you're experiencing in terms of your visual aid, that reddish color or that, that whitish bright light, those wavelength distributions are directly connected to the temperature of the objects. And because of this, observation that red hot objects are cooler than white hot objects, a scientist named Max Planck basically said or theorized that the energy that's released from these objects was occurring in basically specific amounts or chunks, these discrete specific quantities, and he called these amounts, these emissions or absorptions, he called them quantum. And a quantum is a fixed amount of energy that can be emitted or absorbed as electromagnetic radiation. And what he said was that atoms, or matter, can absorb and release energy only in whole multiples of these quantums. So basically, you can have 1 quanta, 2 quanta, 3 quanta, etc. So the relationship between energy and frequency is represented by this equation here, which basically expresses energy with respect to a constant known as Planck's constant, which you can see right here, and frequency. So the energy of the light being absorbed or released by the atom or by the matter is directly proportional to the frequency of that light. So this equation connects our light and the actual waves with an actual energy value. So all light therefore has energy, and this led to other experimentation and other discoveries, as we'll talk about here in a second. But before we do that, let's go ahead and let's look at a few of the details. Remember, energy here for this equation, it's calculated in joules. Why? Because Planck's constant, as seen below, is in joules. Remember that frequency here, it's in hertz. Remember, that can be looked at as inverse seconds as well. So when you're going and doing a dimensional analysis or a unit analysis on your problem, all of your units should cancel out. Don't be intimidated by the hertz unit. So let's go ahead and let's look at some calculation utilizing this equation. The blue color in fireworks is often achieved by heating copper 1 chloride to about 1200 degrees C. The compound then emits a blue light having a wavelength of 450 nanometers. What is the increment of energy that is emitted at 450 nanometers by the copper 1 chloride? So basically what they want us to do here is they want us to calculate our energy, and we know from previous items that energy is equal to H times our frequency. However, we have not been provided frequency, we have been given wavelength, and we've been given a wavelength of 450 nanometers. Now, we know that we can interrelate wavelength and frequency by the following equation. Okay, so C equals lambda times nu. So we know our speed of light times 10 to the 8 meters per second. We know our wavelength because they gave it to us, so 450 nanometers. And we do not know our frequency. This is actually what we want to solve for in order to plug into the initial equation here. So this is a two-part question. We need to first calculate our frequency and then subsequently calculate our energy. So if we rearrange this equation here to solve for frequency, we're going to end up with frequency is equal to C divided by lambda. Now, something we need to check before we plug anything in is to make sure that our units match. And in this case, we have nanometers and we have meters. So we know that those units are not going to cancel. So we know that we need to take the 450 nanometers and we need to convert it into meters. So there are 10 to the 9th nanometers for every 1 meter. That's our conversion factor. We go ahead and convert that, and that's going to give us 4.5 times 10 to the negative 7th. The units are obviously going to be in meters because nanometers and nanometers cancel. So now we can go ahead and plug this value in for our wavelength. So if we go ahead and now solve this problem, we have our frequency equal to 3.0 times 10 to the 8th meters per second divided by 4.5 times 10 to the negative 7th meters. Okay, we go ahead and plug this into our calculator, and it's going to give us 6.7 times 10 to the 14th inverse seconds, or hertz. You could express it either way. So this is our frequency value. Now we're going to take this frequency value and we're going to plug it into the energy equation. So E equals H times our frequency. So we know our H value, that is Planck's constant, and so that is going to be equal to 6.6262 times 10 to the negative 34 joule seconds. And our frequency is 6.7 times 10 to the 14th hertz, or inverse seconds. So we go ahead and plug that into our equation. 6.62662 times 10 to the negative 34 joule seconds times 6.7 times 10 to the 14th inverse seconds. Okay, we go ahead and plug this into our calculator, and that gives us an energy value equal to 4.4 times 10 to the negative 19th. Okay, if we do a unit evaluation, notice seconds are going to cancel, so joules are the unit of energy that you will get. That relates directly to this light that is being emitted when the firework explodes. As always, make sure that anytime you're doing these types of calculations, you look at what you've been given, what you're trying to solve for. Make sure that you're paying attention to the units that are provided in what you're given, and make sure that they're going to make sense in terms of cancellation when you go to do your unit evaluation for your calculations. So after Max Planck shared his findings with regard to energy and the frequency of light, other scientists went ahead and utilized it to explain other phenomena that were not able to be explained by simple wave theory. Albert Einstein was one of these researchers. So basically, the idea or the concept that Albert Einstein utilized Max Planck's information or his findings to explain was the photoelectric effect. So what is the photoelectric effect? Basically, what the photoelectric effect is when you have a metal with a clean surface and you shine light onto that surface, sometimes electrons will become ejected or will be ejected from that metal surface. Now, what the findings were with the photoelectric effect is that there was a minimum frequency required to make this happen. Notice we have different waves or different values of light with different wavelengths and subsequently different frequencies that are being shined on this potassium metal surface. Certain wavelengths will not allow electrons to be ejected from the surface. However, notice that there are other light waves that do have the appropriate frequency to cause the ejection of these electrons. Albert Einstein took the idea that Planck shared, which was that the light has a specific energy that's directly related to its frequency, and used that to explain why these electrons were being ejected with certain lights but not others. So one of the things that Einstein concluded here was that the energy needed to get these electrons to leave their orbitals and exit that atom was very specific. It was a specific amount of energy required, and he called these waves of light basically energy packets. Or another a vocabulary word that he settled on were photons. So basically, these waves of light were photons of energy that were striking the surface of the metal. And when that energy struck the metal surfaces, the atoms in that surface, the electrons that were in those atoms could potentially be excited and expelled from the surface of the atoms. So basically what he did is he showed how the frequency of that light did directly affect the energy being applied to the metal surface and subsequently causing an effect on the individual atoms. Einstein also correlated Planck's research with his E equals mc squared theory of relativity work, and was able to actually show that not only do these particles of light or these photons have energy, they also have mass. So what he did is he combined these two equations. As you can see here, we did a little bit of rearranging. We solved for mass with the E equals mc squared equation. We subsequently substituted E utilizing our relationship between frequency, wavelength, and the speed of light. Okay, and then what we did is we subsequently solved for that by canceling the appropriate repetitive units, which in this case is the speed of light, and that gave us this equation here. Notice we have mass associated with these photons. We have Planck's constant, we have a wavelength, and we have a speed of light. So mass is a component of light. So light has mass. That's what we just said. Not only do they have specific energy quanta, they also have mass. And we're going to talk more about this a little bit later. But for now, basically these two scientists, Max Planck and Einstein, utilized these concepts of energy or light having energy to explain some effects that were not previously understood. Now, let's go ahead and do some practice problems and apply some of these concepts to questions that we might see in an AP chemistry test or other types of problems. Let's go ahead and look at this question here. So a laser light has a wavelength of 7.8 times 10 to the 8th meters. What is the relative mass of this photon of light? So we just discussed that light has mass. So we can utilize the equation that was shared in the previous slide to calculate the mass of any photon of light. So we know that mass is going to be equal to Planck's constant divided by our wavelength times our speed of light. So what have we been given? Well, we know the constants. We know h, which is Planck's constant, 6.6262 times 10 to the negative 34 joule seconds. We know C, which is 3.0 times 10 to the 8th meters per second. And we've been given a wavelength of 7.8 times 10 to the 8th meters. Okay, so we've been given these three values. So if we look at their units, the units look acceptable. We have meters and meters, and our two constants here, seconds and seconds, and the two constants there. So it looks like we have appropriate units to plug into the equation over here. So if we go ahead and do that, m is going to be equal to 6.6262 times 10 to the negative 34 joule seconds divided by 7.8 times 10 to the 8th meters times 3.0 times 10 to the 8th meters per second. Okay, so if we go ahead and plug this into our calculator, this is going to get 2.8 times 10 to the negative 51. Okay, so now that we have our numerical value, we need to go ahead and take a look at our units. So if we go ahead and pull the units away from the numbers in this calculation, what we end up with is joules times second on top and meters times meters over seconds on the bottom. So if you look at this unit evaluation, what you should immediately notice is that none of the units on the bottom are canceling. In fact, the units on the bottom end up being meters squared per second, which at this point is maybe a little bit confusing. When we divide the meter squared per second into the joules times second, that actually ends up giving us joules times seconds squared over meters squared. So at this point, what you should notice about your units is that there are no mass components to them. There's no grams or kilograms or anything else. So something that you need to pull from your memory or have your memory jogged by what I'm about to tell you is that joules is related to mass, and it's related to mass in a very specific way. So 1 joule is equal to kilograms meters squared divided by seconds squared. Okay, so 1 joule is equal to this. So I have joules over here times seconds squared over meter squared. So when I plug this value in for my joules over here, I will be able to get my kilogram or my mass units. So if I go ahead and do that, I'm going to have, instead of my grams, I'm going to have kilograms meters squared per second squared times seconds squared over meter squared. Okay, seconds squareds cancel, meter squared and meter squared cancel, and kilograms are left over. So this photon of light has a mass of 2.8 times 10 to the negative 51st kilograms. So an extremely, extremely small quantity of mass. Okay, so whenever you're doing these types of problems, remember that you want to pay attention to your units. Do not get discouraged when you see something like this, where you don't end up with any mass units. Just remember that the joule is related to mass via this equality. Plug the appropriate numbers in, and you subsequently can get the proper units for what they're asking.